Thank you all for coming here today. I am Devika. I'm a program associate at Science Gallery Bengaluru. Today, the format will be a lecture followed by a panel discussion. And the lecture will be delivered by Anil Ananthaswamy. Anil Ananthaswamy is an award-winning science writer, author, and former deputy news editor at The New Scientist. His writing spanning physics, neuroscience, quantum theory, AI, and cosmology has appeared in Quanta, Scientific American, Nature, Discover, and other publications. He is the author of 4 books: The Edge of Physics, The Man Who Wasn't There, Through Two Doors at Once, and Why Machines Learn. His work has been recognized by Physics World, Smithsonian, Forbes, and the Penn EO Wilson Literary Science Writing Awards, among others. And for our panel discussion, we have Arindam, Ghosh, and Shobhana Narasimhan. Arindam Ghosh is JRD Tata Chair Professor of Physics and the convener of the Quantum Technology Initiative at the Indian Institute of Science in Bangalore. He is an alumnus of the University of Cambridge and has been a visiting research fellow in nanotechnology at the T.J. Watson Research Center of IBM. Arindam co-created the vision document for India's National Quantum Mission and led design of the undergraduate quantum education for over 9,000 technical colleges and universities in India. Shobhana Narasimhan is a physicist in the Theoretical Sciences Department at the Jawaharlal Nehru Center for Advanced Scientific Research in Bengaluru, where she heads the computational nanoscience group. In her research, she uses techniques of quantum mechanical density functional theory to understand why materials have the properties they do. This understanding is then leveraged to design novel nanomaterials for targeted applications. Her work is of both fundamental and technological interest. I would like to mention that both Arindam and Shobhana are part of our next exhibition season's advisory board. The next exhibition season is Quantum, which... Anil also are part, both of them are, all three of them are part of the advisory board.
Shobhana, for those of you
part of the advisory board, and this sort of will shed light into what our next exhibition will entail. Thank you all for coming here today. Over to you.
So thank you for coming. About 15 minutes ago, there were 3 people, so I was wondering if we were going to have the lecture at all, but it's good to see it filling up. Arindam, the third panelist, he's going to join us in a little bit. And so I'm Anil, and that's Shobhana there, for those of you who don't know her. So this talk is basically about why the 2025 Nobel Prize in Physics was given to the 3 people who got it, and I'll come to that. But I thought instead of just talking about the physics of the prize-winning, the physics that got the prize, I thought I'll essentially give you a sense for all the, not all, but the important kind of historical and conceptual ideas that led up to this prize. Because, if you just look at the 2025 Nobel Prizes in physics and just try to read about why it was given to these people, it's kind of hard to figure out what is so amazing about it. But if you look at the history of the field, and if you get a sense for what quantum mechanics is, then it's much easier to appreciate the import of this prize. So can I get a show of hands to see how many of you have a basic understanding of quantum mechanics? Oh, okay, quite a lot. Fantastic. So, but because there are at least half or more people who don't, and it's such a weird topic that I thought I will start by giving you a sense of a bit of a sense for how strange the quantum world is, right? And then we can get into some specifics. And most of you would have heard about something called the double slit experiment. This is an experiment that was first done in the early 1800s by an English physicist, polymath called Thomas Young. And this is an idealized depiction of that, and it's actually a very, very simple experiment, and I'll explain it. And then we will switch to what is called the quantum version of this, and you'll start seeing what a weird thing it is. But the basic experiment is something very straightforward. You have an opaque screen into which are cut 2 slits or openings, right? And on one side of the opaque screen, you take, let's say, a beam of red laser light. It could be any color, but let's say a laser light of a single frequency, and you shine that laser light on the opaque barrier with the two slits, and your kind of common sense intuition tells you that if you just shine light on a screen which has two slits, on the other side you should probably just see two strips of light, right, forming on a screen further away. And it turns out that if you do this with, let's say, red laser light, you don't get two strips of light, rather you get this pattern of bright and dark and bright and dark. And so the screen which you're looking at, where you're seeing the pattern of light and dark bands, think of that as a photographic plate, right? So that photographic plate is recording light as it falls. So the dark regions are where most of the light is falling, and the white regions are where no light is falling, right? So if you were to do this, you will see that pattern, and that pattern is what is called an interference pattern. And the only way to explain that pattern is if you assume that light is made of waves. So the wave of light hits the two slits, and then from each slit on the other side, you start getting what's called a diffraction pattern. Like each two sets of waves start emanating out from the other side, and as they expand, they start interfering with each other. And whenever you have two sets of waves interfering with each other, you get this interference pattern where the crest of one wave, the point at which the wave is the highest, ends up aligning with the crest of another wave, and you get constructive interference. And if you have the crest of one wave and the trough of another, so the highest point of one and the lowest point of another end up being at the same place at the same time, you will get destructive interference. And so this would be very familiar if you were to think of being at the beach, and let's say you have a wave barrier, like a concrete wall with two openings, and the ocean wave is coming at you from the other side, and the wave hits the breaker, and then from those two openings you'll see two sets of waves coming out. And as these two sets of waves spread, you will start seeing them interfering, so the water starts going up and down in a certain pattern. And this is very, very obvious when you look at water, because we are intuitively familiar with how waves behave in water. But this light is also doing exactly this. So throughout the 1800s, physicists became convinced that light was actually wave-like in nature, right? And through the late 1800s, we started having theoretical accounts of why light should behave this way. So Maxwell came up with his theories of electromagnetism, and it was pretty firmly established that light is wave-like in nature, and this experiment was one of the standard ones that you would do to show light's wave nature, right? But then, and I'm going to come to quantum mechanics in a bit, but there are terms I'll use here which will borrow from ideas in quantum mechanics. So bear with me for a while. So let's assume that we can turn down the intensity of the laser light, right? So you have this little sort of source of laser light, and of course you can't do this at home, but assume you can somehow in the lab just turn down the intensity of the laser light so that finally all you're getting is one single pulse. I shouldn't even use the word pulse. Let's say one single particle of red light, right? And I have not yet mentioned to you that light can be made of particles, but assume that what you're getting is a little unit of energy of red laser light, such that that unit of energy cannot be subdivided any further. It's the smallest unit of energy that is possible, and you cannot subdivide it any further, right? So now you're getting something like little tiny bullets coming out of this laser light, this source that you have, like single units of light. And you send them out 1 a second, let's say, right? So they're coming out like particles now, and you have the same photographic plate on the other side. And the question for you is, if you did this for about an hour, so that you send, 100,000 of these sort of small units of red light, what would you expect to see on the other side? Knowing that the unit of energy now cannot be divided any further, right? Before we said that in order for interference to happen, something should go through both the slits, right? So we treated light as a wave, and that light went through both slits and created the interference pattern. Here we are saying that we now have single units of light, and cannot be subdivided any further. Our intuition is saying that it must go through the left or the right slit. What do you expect to see on the other side?
Photons.
No, photons are the term for the single units of light, but what do you expect to see on the photographic plate? What pattern do you see? Dots forming, but what dots in what pattern? You kind of intuitively feel like now you should start seeing two strips of light because they have to go through one or the other, and then they'll hit the photographic plate on the back, so that those two strips should kind of line up behind. This is sort of what we were saying about classical light also before, right? That we thought that the light would just go through one slit or the other, and on the other side you should see two strips. You didn't. In this case, because we have now said we are going to turn down the intensity so that it's coming out like single particles, which are called photons, by the way, that's the right term. So these photons of light are going through one slit or the other. Again, we are speaking intuitively with our classical intuition of the everyday world. You expect to see two strips of light. And I'll give you a couple of examples of what might happen if you, for instance, closed one of the slits, right? If you close, let's say, the right slit, and now you're shooting single particles of light, this will be observed. You will see a pattern like that behind one of the slits, right? If you close the other slit, you would see this. So the question now is, if you had this, what would you see? If both slits are open, what do you see, right? Our intuition says that we should see this. Intuitively, do you agree that this is probably what should? It turns out, this is quantum mechanics, and anytime somebody asks you, do you expect to see this? Your easy answer is no. This is what you see, right? So you see basically, again, an interference pattern, right? You see particles of light, individual photons of light hitting the photographic plate, and this pattern emerging over time, right? But the curious thing is, you're only sending one particle at a time, right? Before we had a beam of light, and you could talk of a wave going through the two slits. You could talk of the two sets of waves that emanate from the other side of the slit interfering. But here the question is, what on earth is interfering, right? Right? Because it's just one particle going through the apparatus at any single time. We can, let's say experimentally, we can guarantee that there's only one particle going through that apparatus at any one time. So it's not like one particle is interfering with another particle, right? So one particle goes through the two slits. We don't know what it's doing. It's ending up on the photographic plate, and it turns out that the way the particles end up on the, let's say you sent 100,000 of them, the 100,000 of them would eventually land in positions that would create that pattern. Something is interfering. It's obviously not that single photon. Well, we can't even say obviously. Let's not make any sort of obvious statements from our everyday intuitions. Something is interfering, and we don't quite know what, right? And yeah.
So what if we just pass, allow one particle and stop the experiment? What would we see?
You'll just see one dot. You can't say any. So I'll come back to that. So do me a favor. This subject is weird enough that let's not do questions during the discussion, only because we'll get sidetracked into all sorts of. Let me just go through this, and then we'll keep track of your questions, because it's a good question. But just keep track of your questions, and we'll come back to it. Okay. I don't want to lose my train of thought because of this weird topic, but more importantly, as we try to answer those questions, we'll go into rabbit holes that will be very hard to get out of. So quick answer to your question: it will just form one dot. But you can't predict where that dot will be. It will be in one of those regions that eventually becomes the constructive interference, but it won't be in a region where you have destructive interference. And that's the mystery, right? And I'll talk about that. So something is going through both slits. And the whole question here is, what is going through both slits? So to understand that now, we need to step back a little bit. So I've just set up for you, this weird experiment that first was done with classical light, right? And it was relatively easy to understand for the physicists. They came up with the theories necessary to explain the behavior of light in everyday scenarios. But when you started dealing with single particles of light or photons, things completely were befuddling. It was unclear what is going through both slits. And for that now we have to really get back to the birth of quantum mechanics. So the birth of quantum mechanics, it really starts in 1900 with Max Planck, showing that certain idealized objects called black bodies. So black bodies are these, as the name says, they're idealized objects that absorb everything that falls, all the radiation that falls on them, and they appear black because of that. And they also emit radiation that is basically only dependent on the temperature of the black body, right? So, and it turned out that in the late 1800s, people they had theories for how these black bodies should behave, but they were using our understanding of classical physics, so Maxwell's theories of electromagnetism, for instance. And the theories were predicting that as the black body is emitting radiation and as it gets to higher and higher frequencies, it should be emitting an infinite amount of energy. And empirically, that wasn't the case. People were measuring these things, and it was certainly not the case that the black body was emitting an infinite amount of energy. And so there was a huge discrepancy between what theory was saying and what experiments were showing. And Planck comes up with this idea that the black body must be both absorbing and emitting radiation in quanta, meaning a quanta here is like, we talked of red laser light. So red light, let's say pure red light is one single frequency. So for any given frequency of light, a quanta here refers to the smallest unit of energy for that frequency, right? So that quanta cannot be subdivided any further. In the case of Planck, he was not really talking about energy actually being energy actually coming in quanta. He was simply talking about the fact that the black body must be absorbing and emitting light or electromagnetic radiation in quanta, so in chunks. And he used that idea to explain why the experiments were actually, or rather, he adjusted the theory to basically explain the experimental observations. So by saying that the black bodies were either absorbing or emitting radiation in quanta, in chunks, he didn't really say unequivocally that energy itself came in quanta. He was just talking of what might be happening with the black bodies. Then 1905, Einstein comes up with a theory to explain the photoelectric effect. So photoelectric effect, all of us now must be familiar with. This is exactly the science behind our solar cells, right? Solar energy, light falls on the solar cell, it ejects electrons, and those electrons constitute electricity. Yeah, that's how we generate electricity from our solar cells. But there was a mystery even at the time in early 1900s where people knew that when light hits a metal, it ejects electrons. That is the photoelectric effect. But the curious thing was, for any given metal, the light had to be above a certain frequency threshold. If the light had a frequency lower than that, that didn't matter how much light you shone on that metal, you would not get any electrons out. As soon as the light crossed the threshold of a certain frequency for a given metal, so different metals would have a different threshold, but for, let's say for silicon, you're shining light on it. If the light that you shine on the metal is above that threshold frequency for that metal, suddenly you start seeing electrons being ejected, right? So, and this again could not be explained with classical theories of light. You could not use classical electromagnetic, Maxwell's electromagnetism to explain this. So Einstein realizes that light has to come in quanta, in the sense that, again, if a certain frequency of light is hitting metal, then that light must be constituted of individual particles, photons of light. So for red light, it would be composed of photons of red light, and each of those photons makes up one indivisible unit of red light. So it's the smallest unit of energy of red light. You cannot divide it any further, right? So, and he was this is when the idea that electromagnetic radiation comes in quanta took root, right? And Planck did not like this at all. In fact, I think, if I remember right, when he was recommending Einstein to be a member of he was giving him a recommendation letter to join the Prussian Academy of Sciences. He basically recommended him very highly, but told the Academy that, Einstein has come up with this theory of quanta for electromagnetic radiation, which is completely wrong, so please don't hold it against him for having come up with this theory. You should still give him the membership to the Prussian Academy of Sciences. And it turns out that Einstein was right, and Einstein wins the Nobel Prize for this particular sort of theory. But the big point here is that energy comes in quanta, right? So it doesn't matter what the electromagnetic radiation is for any given frequency of electromagnetic radiation. So light is electromagnetic radiation. For any given frequency, you can calculate what that smallest unit of energy for that frequency must be, right? And that is quantum of energy. That is that quantum of energy. And so suddenly our notion of what light is changed. It went from light is wave-like, which was the idea that dominated all of the 1800s, to this idea that, oh, light is actually composed of particles. And this debate about whether light is made of particles or light is made of waves actually predates to Newton's times. And Newton was a big believer, he advocated the particle theory of light, but even in Newton's time, there were other physicists who were arguing that light has to be made of waves. So this debate had been going on, and by the time we come to quantum mechanics, it turns out that it's actually both. There are certain situations where you have to treat it as if it has wave-like properties, and there are certain situations where you have to treat it as it having particle-like properties. So this was the beginning of the idea of reality, at some very basic level being quantized, that things become indivisible. So normally when we think of anything, we keep dividing it into smaller and smaller chunks, and we think that that division keeps continuing ad infinitum all the way down. And this was the beginning of the idea that reality actually, at some point, you can't break it down any further, that there is some sort of chunking going on, right? Something similar happens in 1913 when Niels Bohr, who had been working on the structure of the atom. So until about this time, the idea that we had of the atom was there was a nucleus, or there is a nucleus, and there are electrons orbiting the nucleus in the way that planets orbit the sun. So imagine the sun being the nucleus, and the planets are going around in various orbits, right? Fixed orbits around the sun. And the general idea was that, atoms must behave the same way, where you have the nucleus, and which has protons and neutrons, and then the electrons are going around in orbits around the nucleus. But there were some huge theoretical problems with this model, and one being that if electrons are moving around the nucleus, then Maxwell's theory of electromagnetism basically says that as these electrons are spinning around, they should be radiating energy. They should be just giving out a little bit of energy, which basically means that over time, an electron will keep losing energy, and it will eventually spiral in and crash into the nucleus. So the atom technically is unstable. At least that model of the atom is unstable, and we know, we are all here, so obviously atoms are not unstable. So there was a big discrepancy between the theoretical model that people had at the time and what they knew empirically. So this is when Niels Bohr, again, based on what had been happening with Planck and with Einstein and others, he argues that electrons cannot occupy. So if you think of the solar system, right? If you think of the sun, we have 8 planets. There were 9, now 8, right? So at each of those planets can be thought of as occupying a different energy level, right? But there is a continuum. It just so happens in our solar system that the planets are where they are. They could have been anywhere. It's a continuum from very near the sun all the way to where Pluto is and beyond. So technically, electrons should also be able to occupy any region, from the outer limits of the nucleus all the way to some far limit of the atom. And Bohr argues that no, atoms can only occupy certain. It's as if you took the solar system and you said, no, you can have planets, but you can have planets only in certain orbits. You cannot have them in intermediate locations, right? And which is not true of our solar system. If you look at another solar system, the planets might be somewhere else, right? But Bohr is now saying that the atom must be such that the electrons can only occupy certain energy levels, or their distances from the nucleus, however you want to think about it, must only be at certain discrete locations. And this was the first sort of beginnings of idea of quantization coming into atomic physics. And this also meant that when atoms can absorb energy or also emit energy, right? Depending on, you can shine radiation at an atom, and depending on where the electrons are, the electrons can absorb energy and go to a higher energy state, or sometimes the electrons will emit radiation and go into a lower energy state. And Bohr also argued that this emission of radiation is also quantized. So if an electron emits radiation, then it will jump from what can be called a high energy level to a lower energy level, but that energy it emits can only be a certain value. It can't take any value. It has to be a particular set of values. So this again was the quantization of the idea of quantization entering atomic physics. So these ideas, right? The idea that energy comes in quanta and that quantization is inherent to reality, this was the beginning of our understanding that reality is like that. But this is the same slide. Light exhibits both wave and particle nature, and energy itself cannot be infinitely subdivided into smaller and smaller chunks, and that there is the smallest unit of energy for each frequency of electromagnetic radiation. This was the basis of the beginning of quantum mechanics. But these were just conceptual ideas. The formalization, the mathematics, the theories, etc., took a lot longer, and the formalization happened. I'm being very coarse-grained here and giving you some very high-level snapshots of what happened. 1924, Louis Devoret develops the wave-particle duality. There are spelling mistakes here. Develops wave-particle duality for matter. So until now, we were talking of wave-particle duality, that light can be either wave-like or particle-like, but light is energy. So now, Devoret comes and says that no, matter also behaves the same way. So this would apply to electrons. Electrons are matter, so the same idea should apply to electrons too. Electrons should sometimes behave like particles and sometimes like waves, depending on what the situation is. So that was one big moment in the history of physics. Then 1925, Werner Heisenberg developed something called matrix mechanics. It's a particular way of describing how quantum systems, such as an electron, behave in the presence of forces, right? And matrix mechanics was really weird for a lot of physicists at the time, because it essentially moved people away from thinking about how physical systems have properties that change continuously. Like, for instance, if you're thinking of a planet's position in a solar system, it could occupy any distance from the sun to Pluto and beyond, and that it could basically be along a continuum, whereas matrix mechanics, by the way it's formulated, only allows quantum systems to exist in certain states, right? It's not a theory that allows for a continuous change in properties. 1926, then Erwin Schrödinger, who was very upset with matrix mechanics because he was, I guess you can call him old-style physicist, even though he's actually one of the biggest exponents of what happened with quantum mechanics, but he really wanted to preserve the old way of thinking of classical physics, and he developed something called wave mechanics, where he shows that if you take the state of a particle like an electron or a photon, and it has a quantum state, let's say the quantum state describes the position of the electron, where the electron is in space and time, right? So he showed that this quantum state will evolve continuously, and the equation that helps you figure out how the quantum state changes continuously over time and space was a differential equation that is named after him. It's called the Schrödinger equation. So he basically says, okay, here's the quantum state of the particle, and I can show you how this quantum state will change with time and space if you use my equation. So this was called wave mechanics. So if let's say the quantum state of the electron showing its position was some state here, he showed that over time this quantum state would behave like a wave, right? And the equation was very nice, and everything seemed to be coming back to the classical way of thinking. People were happy, I think, at that time, at least Schrödinger was. And then it turns out Schrodinger himself then shows that wave mechanics and matrix mechanics are one and the same thing. They're just two different ways of looking at the same thing, which basically meant that matrix mechanics was correct, that the underlying reality has states that actually jump around. They don't transition continuously from state to state. So there's something weird going on. Wave mechanics is suggesting that the quantum state evolves smoothly, right? There is some continuous variation from point to point, whereas matrix mechanics is saying, no, hang on, that's not the case. So then the question became, what on earth is this, quantum state? If on one hand you're saying that the properties of a quantum system are discrete, that they don't occupy a continuous space of states, and on the other hand you have this wave equation that is saying that the quantum states changes continuously, then the big question became, what is that quantum state that Schrodinger had in his equation? Schrodinger believed that it basically represented some smeared out physical distribution of an electron, right? If you are looking at the position of an electron, and if the quantum state is capturing the position of an electron, then in Schrodinger's mind, it was basically something that told you how the location was smeared out, right? You could, by just looking at the quantum state. But that wasn't the case. It wasn't actually correct, his intuition. Same year, Max Born then shows that the quantum state, which is called psi, or it's also called the wave function, and these two terms will keep coming back, especially the word wave function. So just keep that at the back of your mind. It doesn't represent a physical wave, right? It represents amplitude. It represents probability. So if you take the square of the amplitude of the quantum state, you can calculate the likelihood of finding an electron somewhere if you choose to look for it there, right? So this is a mouthful, but it's worth sort of pondering on it, that this wave function, the quantum state that the Schrodinger equation tells you how to evolve over time and space, doesn't tell you where the electron is. It basically tells you that if I choose to look for the electron there, I can use the quantum state to calculate the probability of finding the electron there. If I choose to look for it there, I might get another probability. So basically, it's telling you that over time, the Schrodinger equation tells you how the quantum state has got smeared over space and time. And that wave function will have some amplitude. You take the square of that amplitude, and that lets you calculate the probability of finding an electron there or there or there. So essentially, you must have heard this term, this phrase in popular writing, that quantum systems can exist in multiple places at the same time. It's entirely unclear whether they do. We don't quite know, but it's definitely true that you can take the wave function, which represents let's say the position of the electron, and you can use the wave function to calculate, if I look for the electron in location A, what is the probability that I'll find it there? If I look for it in position 2, what is the probability that I'll find it there? If I look at it somewhere else, what is the probability that I'll find it there? And the wave function will let you calculate the probabilities. Let's say it gives you probability 30%, 0.3 for being there, 0.3 for being here, and 0.4 for being somewhere else. So 30%, 30%, 40%, right? For any given electron, if you choose to look for it in one location, you may or may not find it there, right? So let's say you choose to look for it in location A, right? And your wave function said, oh, there's a 30% chance you'll find it there. So literally there is a 30% chance of finding it there. So if you did this same experiment over and over again with 100,000 identically prepared electrons, then 30% of those you'll find in location A, 30% you'll find in location B, and 40% you'll find in location C. Any given electron, you have no way of saying where it will be. It will be either in A or B or C, right? With those probabilities. Does that make sense? And this wave function, turns out, is exactly what's going through the double slit. Mathematically, So mathematically, it's the wave function that is going through the two slits, right? We were earlier asking what is going through the two slits. We can't make sense of this if we talk of it as one single photon going through one slit or the other slit, right? But if you take each photon, represent it using its wave function, right? The state of the photon, which is representing the position of the photon, and then you let that wave function evolve using Schrodinger's equation, you will see that wave function spreading and hitting the two slits. This is all happening mathematically. It's very unclear what's happening physically. Mathematically, it's that wave function that hits the two slits, behaves exactly like a wave would. On the other side, you get a diffraction pattern of the wave function. So, and there are two components of the wave function that start spreading. They interfere, and when they interfere, this thing that you see at the back now think of that as the probabilities that the interfered wave function is telling you where the electron might be. So where there is a peak, that's where the electron is most likely to be. So at the very center is the highest probability. Then the probability drops. And then you come a little bit further away from the central peak, you get two other peaks, right? Slightly higher in height, but nonetheless peaks, right? So now those peaks are essentially telling you that those are regions of high probability. The low, so the troughs of that interference pattern are telling you that the likelihood of finding an electron there is very, very low, right? So now the detector is essentially looking for the electron everywhere, right? Or in this case, the photon. So I'm going to be mistakenly switching between electrons and photons. It doesn't matter. They're going to behave exactly the same. Richard Feynman had a very nice way of talking about this. He was giving a lecture at Cornell where in 1964, where he starts by talking about electrons, and then he says most of the theory that we have, most of the early work has been talking of, I forget, basically the point he was making was don't get worried about the fact that we switch between photons and electrons. The only thing that's true is that both of them behave in the same way. They're both screwy. So that this is, both of them screw with your mind in the same way. So any quantum particle that is being sent through the double slit represent its position with a wave function. Let the wave function spread as a physical wave would. Mathematically, then you let it spread all the way to the location of the screen. The two components of the wave function interfere, and you get an interference pattern in the math. Then the math is telling you what are the probabilities of finding the electron at the location of the screen. So the entire screen acts like a detector now. It's basically looking for the particle everywhere, right, over the area of the screen. And it turns out that those probabilities that the math gave you bear out exactly. Again, if you send 100,000 photons one by one through the double slit, one by one, right? So the one photon is not interfering with another photon. It's just one photon going through the double slit. Its wave function goes through. The wave function ends up at the screen, and that wave function tells you that, oh, the photon has a 30% chance of being in the center, 20% chance of being in, sort of two steps on either side of the center, and so on, and maybe almost zero chance in regions of destructive interference. So any given photon will only go to one of the regions of constructive interference and will avoid, I'm using language that is slightly imprecise, we don't quite know what the photon is doing, but essentially it will end up in regions of, in one of the regions that is supposed to be where constructive interference happens, and it will almost never be found in a region where there's destructive interference, right? So if you send a whole bunch of photons, they will all go to different places, but they will go to places where there's constructive interference, and they won't go to places where there's destructive interference according to the wave function, right? And you will see the interference pattern. What is really confounding is that we really don't know whether this wave function is something that is just representing our knowledge about reality, or is it something real in and of itself? And this is a huge debate in the foundations of quantum mechanics, whether the status of the wave function, is it really something physical that is going through the two slits, or whether the wave function just represents our knowledge. So in kind of philosophy of physics terms, you would say, is the wave function epistemic, in the sense that it is representing our knowledge about the physical world, however inadequate that might be, or is it ontological, meaning that it is actually a component of the real world? And depending on which view you take, you get different interpretations of quantum mechanics, and depending on which view you take, you answer some conundrums and you create others. So neither of those two positions are completely without problems. There are lots of interpretations of what's happening underneath the math, and none of them have been unequivocally verified by experiments. So, but for our purposes, let's just keep the idea of the wave function in mind, right? Okay, so this brings us to this idea of the quantum classical divide, and this is going to be relevant for the whole issue of this year's Nobel Prizes. So it was very clear that the smallest components of matter, energy, photons, electrons, neutrons, even atoms, behave according to the laws of quantum mechanics. But what about large molecules, right? Or even larger chunks of matter? It's very clear from our experience of the everyday world that our everyday world is not quantum. And nothing in our everyday experience behaves quantum mechanically. And by quantum mechanically, those two things we were talking about, right? One would be that things are quantized, that things happen only in discrete chunks. In our experience of the everyday world is everything is continuously distributed. The other thing is this idea that when you're thinking about the double slit experiment, we can't talk of the quantum particle going through either the left slit or the right slit. We can only talk of it as something having gone through both. What has gone through both is the wave function. And once the wave function goes through both, the photon itself turns out to be, there's a term, technical term that is used for it. It turns out to be in a superposition of having gone through the right and the left slit. Right? This doesn't make any sense in the context of our everyday world. If there were two openings here in the wall and I threw a cricket ball, it will either hit the wall or it will go through the left opening or the right opening. It's not going to behave as if it is in a superposition of having gone through the left and the right opening, right? So in everyday sort of experience, things don't behave quantum mechanically. So there is obviously something happening with the physics of the world where at the very small scales we know nature is quantum mechanical, that atoms, electrons, photons, even relatively molecules, at least at that time, we knew that molecules also behaved quantum mechanically, but somewhere certain things transition. They stop behaving according to the rules of quantum mechanics, or do they? And that's the question, right? It turns out that this argument has been going on. Niels Bohr, for instance, argued for an operational definition of this divide between the quantum world and the classical world. He basically said that any apparatus that is making measurements of a quantum system is by definition a classical system, right? So if you have a measuring device that is looking for where a photon is, then that measuring device is by definition classical and works according to rules of classical physics. And the system that is being studied is the quantum mechanical system. And this gave rise, this was part of a larger Copenhagen interpretation of quantum mechanics. And in this particular interpretation of quantum mechanics, the quantum classical divide is arbitrary. You come up with basically your apparatus determines where that divide is. And in the Copenhagen interpretation, there was another big issue, which is that the measurement, which in our case was the photographic plate, right? The photographic plate in the double slit experiment is looking for the photon, and that is a measurement. That is trying to see where the photon is, and it's essentially doing a measurement. And just before the photon hits the photographic plate, its wave function is smeared out. It's this complicated wave function that is telling you where you might find the photon if you look for it. But the moment the measurement is made, the photon ends up in one of the possible locations. It's not everywhere. It's not in all places at once. It's in one place, right? It goes from being a smeared out wave function to something that is telling you that the photon is here, right? The wave function becomes what's called localized. So, and this whole thing is called, or you can say the wave function collapses from being smeared out to being localized. And the Copenhagen interpretation basically said that it's the act of measurement that causes the collapse, right? So, measurement is important. In this particular way of thinking about it, measurement is causing the collapse. Until then, the quantum system can exist in a superposition of states. And in the double slit, the superposition of states was simply the photon going through the left slit and the right slit at the same time, right? But there were a lot of people, even today, who are very, very unhappy with this idea that measurement or observation is relevant for the behavior of reality, right? It's like the act of observation is what literally is creating reality or making reality happen. And a lot of people are unhappy with that. And there are another class of theories, for instance, I'm going to just give you a couple of examples of the interpretations. There were people who came up with these things called collapse theories, where the argument is that these wave functions are spreading, and depending on the mass of the system, right? Like if it's just, so whatever quantum system you're studying, the quantum system will have some mass, and depending on the mass of the system, the wave function will randomly collapse. And the act of measurement simply discovers the outcome of the collapse. So reality exists independent of observation or measurement, and observation or measurement simply discovers the outcome of whatever is happening in the quantum world. Right? So this is just another way of thinking about what might be happening in physical reality. The collapse theories essentially provide a relationship between the mass and the likelihood of the wave function collapsing, which is then discovered by observation. It essentially is giving you some sort of mass scale at which the transition happens from quantum to classical, right? So if the mass scale starts getting beyond a certain point, then it becomes more and more likely that the wave function will collapse and you will end up with a classical system. And so collapse theories imply that there is a quantum classical divide that depends on the mass of the system. But the important point is, so collapse theories are not standard quantum mechanics, in the sense that they are an additional, they are an add-on to the standard quantum theory. Standard quantum theory does not have anything to say about collapse. All it says is that when you measure, you cause collapse, but it doesn't tell you how, why, none of that stuff. Collapse theories are putting in a mechanism to cause collapse, and then that is discovered by measurement. So collapse theories are an augmentation to standard quantum theory. And in standard quantum theory, there is no quantum classical divide, right? And the idea is that standard quantum theory might be universally applicable as long as the quantum system that you're studying is suitably isolated from its environment, right? So it can get bigger and bigger and bigger, and it will still behave quantum mechanically. And this is where, this is all leading up to what happened with the Nobel Prizes. But the double slit experiment itself gave people a chance to test out this idea that quantum systems can keep getting bigger, and you should still observe quantum mechanical behavior. So in 1999, for example, there was a group in Vienna, Anton Zeilinger's group, that did the double slit experiment with these things called C60 molecules. These were 60 carbon atoms in one molecule, and they were sending these molecules one by one through the double slit, and you were beginning to see the interference pattern on the screen that is detecting the molecules, right? So essentially, instead of single photons of light, now you had these large molecules acting as if they were going through both slits at once, right? They were in a superposition of going through one and the other slit, and then their wave function interfering on the other side. So they were acting quantum mechanically. 2012, another group, Marcus Arndt, who was actually Zeilinger's postdoc, showed interference for molecules up to 1300 atomic mass units, and that group has been upping the game. I think the latest now, 2013, they managed to do it with molecules with 10,000 atomic mass units, so 810 atoms in that molecule. That's huge now. These are really, really big molecules. 2019, they have gone up to 25,000 atomic mass units, and they are still observing interference. But these experiments become harder and harder and harder, because all sorts of other complications start arising as the mass of these systems gets bigger. But nonetheless, they've been able to show that they haven't been able to see any quantum classical divide, even if you've gone up to 25,000 atomic mass units. So as of now, with the double slit, you can send pretty big molecules through that. It's like throwing cricket balls through the two slits and ending up with an interference pattern of the cricket ball's wave function on the other side, where you can't predict where the cricket ball will go. You can only talk in terms of probabilities of where it will go and land up on the other side. It's like you have 10 catchers spread out on the other side waiting for the cricket ball, and you can only say, oh, there's a 10% probability it will go towards this catcher, and 10% probability it will go there, which again is not how our classical minds work. But if quantum theory holds universally, if you could create a system where you had people throwing cricket balls, two slits, catchers on the other side, all completely isolated, first of all prepared quantum mechanically and then completely isolated from everything else, the whole system technically, theoretically should behave quantum mechanically. We don't know that. We can only work with up to molecules of this size so far, right? But this is already very impressive. These are very huge. So let me just show you So this is a movie that Arndt's group made about these macromolecules going through a double slit, and they are showing and these molecules are tagged with a fluorescent marker, so you can see them landing on the screen on the other side. So you can see that in the beginning, the interference pattern is not very obvious, that the particles are just they seem to be going all over the place. But as the image develops, you see that they're only going to certain locations and not going to other locations, right? All, of course, within limits of experimental error. Anyway, that's an actual sort of experimental movie. So this was just to set up the quantum weirdness, some basic ideas about quantum mechanics. And now I want to talk about the topic of this year's Nobel, but the history of the conceptual ideas that are there in the physics that was done by the physicists who got this year's Nobel. The ideas go back a long, long way, all the way to 1927 when Friedrich Hund identifies this idea of something called quantum tunneling. Again, so you have to first start with your sort of intuitions about the classical world. Again, if I throw a ball at that wall, no matter how many times I throw the ball at that wall, and no matter how hard I throw it, it's always going to bounce back. There's there's zero chance, unless you fire it with such high velocity that you break the wall. Let's say you're just chucking the ball, there is zero chance that the ball will end up on the other side. Whereas that's not true in quantum mechanics, right? In quantum mechanics, if you use that analogy, sometimes the ball will end up on the other side of the wall, right? And so, but this has a more specific meaning in the context of quantum mechanics. So here, think of the wall as some sort of energy barrier, right? So if you think of a hill which represents the energy landscape of a system. You have a ball here, and this is the hill, and let's say you roll the ball right this way, and depending on how fast you roll it, it's going to go up the flank of the hill a little bit. But if it doesn't have enough energy, it'll roll back, right? You have to give it the appropriate amount of energy for it to go all the way up to the top and then come down on the other side. Which means that the ball has to have enough energy to go over the hill and back on the other side. So if the hill represents a potential or a peak in the energy landscape, then whatever the object is on this side has to have enough energy for it to, in a classical way of thinking, has to have enough energy for it to go over and come out on the other side. Otherwise, it will never be able to go over the hill, right? In quantum mechanics, even if the hill is high and if there is some particle here with some energy that classically will never be able to go up and come out on the other side, occasionally it will just literally tunnel through. Well, not literally. It will, in a manner of speaking, it will end up on the other side. It's as if it tunneled through the hill and ended up on the other side. So that's what. Let me show you something. Okay. So the best way to understand this now is, let's say you have a barrier, which is the potential hill. So the potential has some height, which is the height of the energy barrier, and some width, which is how thick the wall is in this case. And on one side, you have a particle with some energy that is moving towards the wall. And the question is, will it get through the wall? And quantum mechanically, what you have to do is you have to depict the state of the quantum system with its wave function. Remember, you can't really talk of where the particle is. You can only talk of the wave function, which is what we were talking about earlier. And you let the wave function propagate along according to the rules of quantum mechanics, which is you use Schrodinger's equation and you calculate how it moves towards the wall. And when it hits the wall, there will be some reflection and some transmission, right? And depending on the exact nature of the hill and the energy of the particle, the wave function will collide with the potential in a certain way, and you will see. I'll show you two different depictions. So this is the wave function. So you will see green and red dashed lines. Those are the real and imaginary components of the wave function, and the solid blue line is the one that is telling you the probability is the square of the amplitude, right? So look at what happens when it hits the barrier. Things happen, and then it starts moving back, right? Look at the solid blue line and its shape on the right side of the potential. Does it ever go above the baseline? Almost not. You can barely see it on the right side of the barrier. Even after collision, the blue line basically remains. The blue line is the one that allows you to calculate the probability of where you will find the particle if you choose to look for it, right? So in this particular scenario, for a certain height of the potential, a certain thickness of the barrier, and a certain energy of the particle, which is depicted by this line here, you have almost no probability that the particle is on the other side, right? So that is one simulation. Now this is another one. The barrier is thinner. Look at what happens. You see the blue line now has a non-zero value on the other side of the potential, right? As soon as it clashes, you will see that. Can you see that? So what that means is that if you had a detector on the other side, sometimes it will see the particle there, right? And in this case, what has happened is the barrier is thinner and the energy of the particle is a little bit higher. It's almost at the height of the barrier. But crucially, it's the wave functions profile that is telling you that there is a non-zero probability that the particle can be found on the other side, right? It's not that the particle is on the other side. What it's telling you is that if you choose to look for the particle on the other side, this time in this simulation, there is a non-zero probability that sometimes you will see the probability, the particle on the other side, right? So this is all so far was done mathematically, and then 1928, George Gamow uses quantum tunneling to explain a certain kind of radioactivity. This is the kind of radioactivity that causes heavy elements like uranium to decay. So when uranium emits a radioactive particle and decays from uranium to thorium, that particle that it emits is called an alpha particle, which is 2 protons and 2 neutrons. Or a helium, it's helium basically. So essentially what's happening is the nucleus is on one side of the energy barrier, and occasionally an alpha particle from the nucleus tunnels through the energy barrier and appears on the other side. So the barrier is simply the barrier that the particles in the nucleus feel in terms of not being able to leave the nucleus. But because this is quantum mechanics, all those particles have their wave functions, and there is a non-zero chance that occasionally one of the alpha particles will have a non-zero chance of being on the other side of the energy barrier, and that's what happens. So uranium will spontaneously eject an alpha particle and turn into thorium, or not one atom of uranium. And this is radioactivity. This is so this was George Gamow explaining how this kind of radioactivity worked, and so it turns out that quantum tunneling is a real phenomenon, and its effects can be empirically measured. But this was just the beginning. Then 1957, Leo Isaki discovers quantum tunneling in semiconductors, invents something called the tunnel diode, which was a big deal at the time. I won't go into the details of the electronics, but just know that these were all seminal sort of discoveries. So this is now we are seeing quantum tunneling in sort of objects that are macroscopic, but it is still quantum tunneling of single electrons. So the things that are doing the quantum tunneling are still very, very small things, in this case electrons, so they can be explained in terms of quantum mechanics. It still hasn't said anything about the quantum classical divide, because electrons we know behave quantum mechanically. So the fact that they tunnel was not surprising. The big thing here was somebody built a device that actually used that phenomenon, right? And then so this is what I was saying. So far, all of the particles that were tunneling were indisputably governed by the laws of quantum mechanics. So nothing, this phenomenon so far did not say anything about the quantum classical divide. And the question was, could this phenomenon be seen in more massive quantum systems, in the sense that could more massive objects tunnel through? It's like we're beginning to ask, can a cricket ball tunnel through this wall, right? So far the answer is absolutely no. But there's a big gap between an electron and a cricket ball. So the question is, where is that? How far can we push this? And in order to understand the answer to that question, we have to go back a little ways. So to the discovery of superconductivity, I think we have an expert on superconductivity here, right? Arnab is? Yeah, you're a Arindam, superconducting expert? Yes, you can say yes. Yes, cool. That's more than most of us. So if you have any serious questions about superconductivity, that's same. So anyway, in 1911, Heike Honest uses liquid helium cooled to 4.1 Kelvin to cool mercury, and then discovers that mercury's electrical resistance vanishes. It becomes what's now called a superconductor, right? But it had to be cooled down to within a few degrees of absolute zero. That is very, very cold. But at that temperature, suddenly that metal becomes a superconductor, in the sense that its electrical resistance vanishes. Honest wins the Nobel in 1913 for being the first to liquefy helium, cooling it down to about 1.5 Kelvin. His Nobel was not for, I don't know if he won the Nobel for superconductivity. Did he? He did. So he got another one.
Just once.
Just once. So in this it was mentioned, 1911 work. Okay. So then what happens? There's a whole bunch of stuff that happens between when was that? 1911 and 1957. I'm just jumping all the way to 1957 because this was when John Bardeen, Leon Cooper, and Robert Schreifer proposed their theory of superconductivity, this so-called BCS after their initials, that the superconducting current that you see in a metal that has been cooled down to within a few degrees of absolute zero, the superconducting current is actually made up of pairs of electrons. These pairs of electrons, so normally in a normal sort of conductor, in let's say room temperature, the electric current is made of individual electrons. And the reason why you have electrical resistance is because these electrons are potentially scattering off each other, and they're also interacting with the lattice structure of the conductor itself, and all of that kind of impedes their flow, and that impedance is the resistance to electrical current. And different materials will have different resistances, but they will all have some resistance and some less than others. So that's why copper is a better conductor than maybe some other material. But what happens in superconductors is that these electrons, which previously were individual and wandering around individually, they pair up, and when they pair up, they suddenly start behaving very, very differently, in the sense that they don't, in a manner of speaking, they don't see the other electrons. They as if there is no resistance to their motion. They're not seeing the lattice structure of the metal, and suddenly all of the resistance to their motion vanishes, and they move in a way that signifies zero resistance to their motion, and hence zero electrical resistance in the material. So, and these pairs of electrons are called Cooper pairs after one of the theorists there. And so these three were awarded the Nobel Prize in 72 for this theory, and then the big things then happened in 60 and 62. You had, I'm kind of bummed that Janvi is not here because I practiced saying this name in Norwegian for her sake, but now I've forgotten what Ivar, I forget. You can pronounce that, guys. It's a Norwegian name. I'm going to call him Ivar. He demonstrates that electrons can tunnel through a thin insulating layer that separates two superconducting films. So you have, let's say, two superconducting films. These are, potentially metal that has been cooled down again to almost to within a few degrees of absolute zero. But those two superconducting metal films are separated by an insulating layer, right? And so essentially current shouldn't be able to flow through it, and Ivar shows that actually electrons can tunnel through that. Even in this setup, electrons can tunnel through that insulating layer. And then 62, this was a big deal. Brian Josephson theoretically shows that, so Ivar shows that single electrons are tunneling through that insulating layer. Brian Josephson's theory shows that Cooper pairs, those paired up electrons, can also tunnel through. So suddenly you have, instead of just one electron at a time tunneling through that insulating layer, you have two electrons as a Cooper pair tunneling through a thin insulator that separates two superconducting films. And Josephson receives the 1973 Nobel along with Leo Isaki, who built the tunnel diode, and Ivar. I had learned this. All morning I spent practicing this name. Anyway, damn. So anyway, these three, this was a big deal, right? Suddenly we have, not just single electrons, but Cooper pairs tunneling through insulating material that is sandwiched between two superconducting films, right? 63, the Josephson effect is verified experimentally. Philip Anderson and John Rowell demonstrate that the Josephson effect is real. Still, the number of particles, whether it's single electrons or Cooper pairs, tunneling through the insulating layer is still small, right? The findings don't have much to say about the quantum classical divide at this stage. This is like, because everything is still fairly well explained by standard quantum theory, and it is not posing any kind of challenge to the idea that, there is a quantum classical divide. So nothing has happened so far. But this is where the work that won this year's Nobel comes in. This is 1985. John Clarke, Michel Devoret, and John Martinis. So John Clarke is the principal investigator, and Devoret and Martinis are, I think they are PhD students or postdocs, I forget. PhD?
One's a student, one's a postdoc.
One is a postdoc, okay. And all of them, I think, are at UC Berkeley. They demonstrate for the first time that large numbers of Cooper pairs can tunnel through a barrier. So same idea. You have a superconducting material on one side, another on this side, and in the middle is an insulating layer. So technically nothing should pass through. But they show that not just single Cooper pairs, but a large number of them can pass through this insulating layer. So the superconducting circuit that they build is 1 centimeter wide, which now we're getting to pretty big sizes, and it contains a Josephson junction. So technically it is now macroscopic. The numerous Cooper pairs in this circuit are described by a single wave function, and this is crucial. So from the perspective of quantum mechanics, all of the Cooper pairs that are there in that superconducting circuit share a single quantum state. So they are described by one wave function, which is what makes them a large quantum system, right? It's not like you're taking each individual Cooper pair and saying it has its own phase. The whole thing is described by one wave function. So what happens to one happens to all in one sense of speaking. It's basically the same wave function, the same quantum state. So it's now a much, much bigger quantum object. And here's a depiction from the Swedish Academy of Sciences Nobel website, and this is kind of cute. So at the top is a depiction of how electrons behave in a regular conductor, right? They basically are all by themselves. They're wandering around and they're scattering off each other, of the material, and they are moving in any given direction because there is an externally applied voltage. So there is a potential difference between one and the other, and that's probably what's driving the electrical current, if there is a current. In a superconductor, you start seeing the behavior that is depicted in the middle column, where you have one superconductor followed by a gap, which is the Josephson junction. That could be the insulating layer, and then another superconductor. And then there are Cooper pairs, basically pairs of electrons that are paired up nicely, and they are just moving through that system. Quantum mechanically, the way you would model it and the way it is in the math is what is shown in the bottom, where all of that stuff is technically one object, right? All of them are described by one wave function, and that is really the key here. That's what makes this now a much, much bigger system than just one Cooper pair or one electron, right? And so this is a cartoon depiction of what these guys did. And so the 1985 experiment, the way they designed it was that single object, which is a large number of Cooper pairs, could exist in one of two states. One was what can be called the ground state, the lower energy state, and then another state which was a slightly higher energy state. They had designed it like that. And technically, in a classical system, if you have something that is existing in a low energy state, it is not spontaneously going to go into the high energy state. It's just not going to do it. It's the same way as saying the ball is going to cross over to the other side on its own. But here, they were able to show that that entire sort of single wave function representing all of the Cooper pairs, it was such that even in the absence of external energy input, sometimes you would see the system transition to the higher energy state, right? And the lower energy state was designed such that there was no voltage across that insulating, the Josephson junction. And the higher energy state was such that a voltage would appear across that junction, right? That was the design of the experiment. They would suddenly see that a system that basically existed in the low energy state would tunnel through a barrier and end up in a higher energy state, and that would appear as a voltage across the Josephson junction, right? So technically there is an energy barrier between the two states, and even with no external energy input, it was able to tunnel through. They also showed that if you did provide external energy input using microwaves, then you increase the chances of this tunneling, because you were giving the lower energy state more energy and increasing its chances of tunneling through and ending up in the higher energy state. But the key thing here was that the system absorbed energy only in certain energies were absorbed, not all energies were absorbed. The quantum system that was absorbing the energy was also doing it in a quantized fashion. It wasn't taking in all the energy, it was only taking energy at certain frequencies, right? So this idea of quantization harkens back to Bohr's, model of the atom, all of that, right? So these were the quantum mechanical observations, but so I basically talked about all this. So these are the three guys who got the Nobel this year, John Clarke, Michel Devoret, and John Martinis. The latter two, Devoret and Martinis, also have become pioneers in, more so Martinis, I think, pioneers in quantum computing, and I'll come to that in a little bit. But the implications for the quantum classical divide, right? This is the topic for us. The superconducting circuit used by Clarke, Devoret, and Martinez was a macroscopic object. So in earlier experiments before this, individual Cooper pairs had been shown to tunnel through the insulating barrier, but here there were billions of Cooper pairs that were tunneling through at the same time. So suddenly the scale was much, much different than anything that was done before. This clearly showed that even macroscopic objects suitably protected from environmental disturbances. So, these experiments have to be done with extreme caution in terms of being in vacuum, being cooled down to near absolute zero to avoid thermal disturbances, etc. They can behave quantum mechanically, right? So, okay, so what happens? So all this seems very theoretical and like, oh, what's the big point? Just like the original Josephson junction stuff, or original tunneling stuff might have seemed like, oh, what's the big deal? And suddenly we had all these devices, right? So just quantum tunneling and the Josephson junction stuff, just to give you an idea, we've had diodes, we've had field effect transistors, tunneling field effect transistors. We have the flash memories that you use in your devices use quantum tunneling. You must have heard, if you have been shopping for big panel, television sets, there are these things called quantum dots. So quantum dots are, they use tunneling. In science, we have scanning tunneling microscopes. So these microscopes are extremely high resolution microscopes that use tunneling. So there is a surface that is being scanned by the tip of the microscope, and it's actually, the tip doesn't quite touch the surface that is being scanned, but it is near enough that sometimes electrons will tunnel through from the surface that is being scanned into the tip of the tip of the microscope, and that current that is induced by the tunneling is the signal that is being used to map out the microscopic structure of the system being studied. So there's a lot of practical applications of tunneling that were already in place well before this stuff came along, right? But now we have billions of Cooper pairs tunneling. So what is the big use? Turns out that the big use is quantum computers, right? So 1999, Nakamura and colleagues developed the first superconducting quantum bit or qubit. So this is a huge jump from all that we've been talking about. So slow me down if you want to. So let me just mention what they did, and then we'll talk a little bit about the actual ideas. So Josephson junction that Nakamura built separated a nanoscale superconducting island from what they called a reservoir of superconducting Cooper pairs around it. So imagine there's an island which is nanoscale. It is separated by a Josephson junction or an insulating layer by another, and outside is some other, larger piece of superconducting material which is a reservoir of Cooper pairs, and they could very precisely control the number of Cooper pairs that could tunnel into the island, right? And so the number of Cooper pairs that ended up on the island could be used to figure out the state of the system. Like, you could say that, I don't know the details here, and Arindam might know. We can talk about this later, but the general idea here is that by precisely controlling the number of Cooper pairs that end up on the island, you can set the system in a certain state, right? You can say that, okay, this number is this state and that number is that state. The key issue here, because this is a quantum mechanical system, you are able to put a system in a superposition of states, right? It's not like, maybe I'll just come to that when I contrast it with classical computing. So we go from the device that they had built to something called qubit. So in classical computing, when we are dealing with information, we are dealing in bits. Bits can be 0 or 1, right? In quantum computing, qubits or quantum bits can be 0 or 1 or something in between. So the state can be a superposition of 0 and 1. So if you want a little tiny bit of mathematics, the qubit state is some alpha times the state 0 and some plus beta times state 1. What this is telling you is that the qubit is not in either state 0 or state 1, it is in some combination of 0 and 1, and that combination is dictated by alpha and beta, such that the probability, when you measure that qubit, the probability that you will find it to be 0 is alpha square, and the probability that you will find it to be 1 is beta square. Okay? This is a very simple depiction of a qubit. Things get more complicated, I won't get into that. I will probably get lost in it as much as you will. So then in classical computing, logic gates operate on bits, right? So we build AND gates, NAND gates, OR gates, all these gates, but they are operating on bits that can be either 0 or 1. And then the gate does something and produces an output which also can be either a 0 or a 1. In quantum computing, logic gates operate on qubits, right? And qubits can be in a superposition of states. So if the input is in a superposition, then the output of the gate might also be in an appropriate superposition. Depending on what the gate is doing, the output itself might be in some other superposition of states, right? So suddenly you have a gate that is not just operating on sort of a 0 or a 1 and producing a 0 or a 1. It's operating on something that is itself in some combination of 0 and 1 and producing an output that might also be in a different combination of 0 and 1 or something more complicated. And depending on what that gate is, the output could be quite a complicated one. In classical computing, then, when you make a Boolean circuit, you make it by interconnecting all these logic gates, right? Which deterministically produces an output given some input. So for the same input, it will always produce the same output, right? And you can analyze that. If you've done sort of digital electronics, you know that you can write the truth table for your Boolean circuit. You know that given certain input, here's what the output should be. It's a deterministic system. In quantum computing, you would do the same thing. A quantum circuit is made by interconnecting quantum logic gates. But then something weird happens. The circuit produces an output that represents a quantum system that is in a superposition. The circuit is basically a whole bunch of quantum gates that have been interconnected. And you're getting inputs that are themselves qubits. Everything is in a superposition, and these things are starting to interact with each other. They start getting entangled, and by the time you come to the output, the output of a few qubits might be a very complicated quantum state that, we haven't even talked of entanglement, but it could be, something that is a very complex superposition of states. And if you think of all these states as being possible answers to whatever computation you did, right? Let's say the circuit is designed to solve some problem. You provide an input. The input is in a superposition of states. So the input itself is many possible inputs. And then on the output side, you get a superposition of states that are technically, you can think of it like this. This is that the entire circuit has simultaneously done multiple calculations at once, and on the output side, you have the whole circuit in a superposition of states. Now you need an answer. So then you do the measurement, and you will collapse that superposition to one of those possible states. So you'll get one answer. You'll get a classical answer at the end of it, right? So the measurement collapses the circuit to one of the many possible states or answers, and you can argue that the circuit has computed all of these answers simultaneously, which is not what a classical computer would do, right? So, and there's a whole lot of stuff that has to be done to make sure that this does anything useful. So the superposition that you arrive at the end should be such that it maximizes the likelihood of the wave function collapsing to the right answer upon measurement and minimizes the likelihood of collapse to an erroneous answer, right? And a lot of it is in the design of the circuit, in the design of the algorithm that you're using. So, but in the end, even a classical computer produces even a quantum computer produces a classical answer. And it might have performed numerous computations in parallel, right? So this is a very, very different way of thinking what is happening inside the computer. So this is where, so right now, this is not theory. There are, quantum computers have been built. I think we are up to something like 100 qubits. Do you know, Arindam? 100, right? About 100. Or just non-super. Gone beyond 1,000. Okay. So connecting 1,000. But the thing. So when we are talking of qubits here, we are talking of what are called logical qubits, in the sense that you have to design the logic of your computation, and these gates represent the logical qubits. But because quantum systems are extremely unstable and error prone, and you can collapse, like an individual gate might collapse from being in a superposition of states to the wave function of an individual gate might collapse. So you need to build in a whole bunch of redundancy in your system. So the number of physical qubits you need in order to implement a logical qubit is much, is I don't know how much more, but it is much higher than the number of logical qubits. Very, very difficult problem. So yeah, I think there are different ways in which you can implement qubits. And what is the Google thing on a chip, the one with 100 qubits? What? Sorry. Google Willow. But that's not superconducting qubit. It is also. Okay. So the point I'm trying to make is this is not just theoretical, right? This is actually being done. And in fact, I don't know if it still exists, but about 4 or 5 years ago, IBM had a 5-qubit quantum computer that they were running, and they gave you access to it via the web. So you could literally go onto the web and use those 5 qubits to design your own circuit and then have it run on the quantum computer on their end. And it was a really nice way of seeing how this thing works. I think they have taken it offline now.
So I heard 1,000 qubits. David Gross, Nobel Prize 2010, he was here. ICTS.
So it's come. Yeah, that's what Arindam was saying. It's come up to 1,000 qubits now. So this kind of tells you that this is where the next Nobel Prizes are going to come in physics. I mean, among other things. So if there is an unambiguous demonstration of quantum supremacy, which is this idea that whatever the quantum computer is able to do, so in any kind of reasonable amount of time, a classical computer will never be able to solve it, right? So something that a quantum computer only a quantum computer should be able to do. That there have been claims of quantum supremacy for certain algorithms, but it hasn't. I think there's still some debate about that. The error correction that I was telling you about, that's still not scalable. So any sort of idea that scales quantum error correction would potentially be a Nobel-worthy finding. And of course, the first useful large-scale quantum computer unambiguously demonstrating quantum supremacy would be Nobel Prize-winning worthy. And then algorithm design, right? Designing algorithms for quantum computers is not the same as designing algorithms for classical computers, because you have to think in terms of the computation proceeding in a way that ends up at the very end in a superposition of states, and you have to figure out how to maximize the likelihood of getting the right answer when you measure, minimize the likelihood of getting the wrong answer, etc. So, key algorithms, any great algorithms that are designed are also worthy of this. There's already algorithms that are amazing, but they have not been scaled up. One is this idea, it's called Shor's algorithm for factoring large numbers. So a lot of today's encryption that keeps our data safe on the internet depends on not being able to factorize large numbers using classical computers in any reasonable time. Shor's algorithm, if given the right scaled up system, could make these encryptions completely useless. So people are already preparing for post-quantum cryptography, like coming up with cryptographic systems that are then, secure against attacks from quantum computers. So, yeah, I'll leave you there. Thank you. So I think we can just start the panel, and whatever questions you have about this talk, and as our blurb says, you can ask Arindam and Shobhana anything. Me, you can only ask me stuff about what I told you on the screen.
So if the double slit experiment which Thomas performed, if it is performed with the normal light,
Yeah.
What would happen?
So you mean just take any light? Yeah. So this light, has all the frequencies in it. So the width of the slits, the separation of the slits, in order for you to get a good interference pattern, is very specific to the frequency of light you're using. So for any given physical configuration of the slits, when you just present white light with all frequencies, you just get a smeared out thing on the other side. I mean, things are interfering, but it's very hard to discern what's happening on the other side. So that's why you use a single frequency, and you design your slits that is appropriate for that frequency, and then you see the interference pattern on the other side.
The interference of the different wavelengths will just overlap, so you will not see clearly light and dark.
Yeah. The constructive region for one might be the destructive for the other frequency, and you'll just it'll all get smeared out.
Shall I go?
Yeah, of course.
The way the human intellect assimilates knowledge, observation, experimentation, logical analysis, superimposition, correlation with other findings, this all looks, cumulatively looks very far the dynamics of the universe. This is not the way to, is there any better way to have an absolute understanding of what is happening in the universe without time-space constraint? We have a knowledge directly when the question is raised.
You want an honest answer? No. I don't see how this is, again, this is going to be a metaphysical answer in the sense that some people believe that somehow our consciousness is not just of this body and that we have access to something that is non-material. I am not one of those people. I really think that all there is matter, and we are also of matter, and everything about us is constituted of exactly the same matter that's everywhere else. And I don't see any way of getting knowledge about the universe without doing these kinds of experiments. That's my position. I'm sure there'll be people who will differ, but Arindam, Shobhana?
No, I think this is far too complex a question to answer at this stage. I mean, what scientists do is essentially break it down into much smaller number of pieces and then try to understand what happens with a very small cluster. The questions that are being asked here is actually a much larger ensemble, and there the complexity is much more, and the kinetics, interactions between different components is far too complex. So I think AI is probably a glimpse of what and how the nature works in many ways, but I think we are not in a position to answer this question.
I think, Shobhana?
I mean, I just think it's impressive that we can understand as much as we do, and that we continue to progress to understand more and more. That in itself I find fascinating. And obviously there are lots of philosophical questions. I mean, will that continue forever? Will we always understand more and more and more? I don't know.
I have two questions. One is about the double slit, the other one is about wave function. So in the double slit experiment, we see that the diffusion is what causes the pattern.
Diffraction.
Diffraction. So basically, light behaves like a wave and spreads out over like a distance. But why does it not happen when it's only one slit? Like, why is it narrow? Like, I understand the pattern.
Oh, even with one slit, there is a diffraction pattern.
The width is the same.
Yeah, I mean because there's no interference, you're only going to get intensity in the center, because the diffraction pattern is it's just a single diffraction pattern, right?
But the end-to-end length is going to be the same, is it? Because
No.
Because in these visualizations, the two slits are always shown as very narrow.
Yeah, that's an idealized visualization just to make people think a little bit.
But in a single slit, the spread of the...
For both single and double slits, the final pattern will be much broader than the slits themselves. Because what happens is the moment the wave falls in the slit, there are wavelets that propagate in all directions. And those wavelets start interfering with each other again. So as a result, actually the width of the resultant pattern is infinite in size. It's just that if you go farther and farther away, then the intensity drops so much that you cannot see it anymore. So the actual pattern is infinitely large, even if the width of the slit is very, very small.
So even if the single slit, you're saying
It is the same thing for the single.
But the pattern is more sharply peaked, and so you see the intensity fall off more sharply.
And my second question was that the thing about wave equation, the meaning of it being that if you take amplitude and square it, it's a probability. Is that a theoretical definition or it's based on experiment?
It has been experimentally verified.
Theoretical sense, is this like...
It is theoretically postulated and experimentally verified.
Okay, but there's a mathematical proof for it, or they just guess that, okay, this could be this, and then they actually...
I don't think there is a proof for it, right? It was Max Born who postulated it.
It was amazing, actually, that he...
It's some form of an ansatz. It's as I said, it's a postulate. It's something that you suggest and turns out to be correct.
And it's been verified to extraordinary precision. There is no doubt at all that that's what it is. Yeah, there is no formal proof. People have tried though, I think, yeah.
First of all, thank you for making quantum physics so simple for even non-physicists to understand. So, forgive my ignorance of a non-physicist here. So, when you told about quantum tunneling and giving the example of disintegration of uranium, if I understood it right, the same particle should tunnel through uranium becoming thorium by giving off an alpha particle. Is it
Alpha particle coming out of the nucleus.
Yeah, is it really considered tunneling? The same entire thing should tunnel through.
What do you mean same entire thing?
No, it's not the whole nucleus.
It's not the whole
that
nucleus.
tunnels. It's a part of the nucleus. It wants to split apart, but it can't. It's for it to split apart that there is this barrier.
Yeah, but tunneling doesn't it mean that the entire...
It can be either. It can be either. It can be either. So here it is, if you would think of it as two parts, one is the thorium and the alpha particle together, they are forming the uranium, and for it to split apart, that is like
An energy barrier.
a barrier.
By the way, actually, also tunneling in quantum mechanical sense is not exactly the same as tunneling in classical sense. For example, if you have a ball, and the example which Anil had given is, it shows that the ball is landing on the other side and it's quantum tunneling. In quantum mechanics, it is in principle possible that a smaller part of the ball is reflected and a larger part of the ball is on the other side. That's pretty much allowed.
Okay, another question. So now that the quantum classical divide is, the border is coming higher and higher when the heavier particles are showing quantum properties, is it possible that by the same logic, even our classical physics on a very large scale will not hold good anymore? just that we don't know?
I'm not sure I understood the
Yeah, can you ask it again?
She's saying quantum becomes classical at some point. Will classical become something else?
Yeah, at a higher level, on a much larger scale, does quantum, the classical physics, also stop?
I mean, it does in some sense, like, I mean, you go from classical gravity to
Exactly.
to,
So I think the only
general
place we can view is the
relativity.
cosmology.
Yeah.
So the black holes, for example, where the classical description breaks down and you get singularity in space-time, and you cannot explain that kind of a situation even with classical physics, right? So, yeah.
There are situations in physics where even macroscopic objects, like black holes for instance, there are situations where, for instance, the curvature of space-time is so much that you cannot just use Einstein's relativity anymore. You also need quantum mechanics, and Shobhana knows this much better. But you are in a position now where you need both theories to work together, and this is actually a very, very big problem right now in physics. That in physical systems where you need to apply both quantum mechanics and classical physics at the same time, things don't work, right? The theories don't work together.
I mean, it also depends what you mean by classical physics. So if you mean like Newton's equations, then if you're going very fast, or if you're very, very heavy, massive, then Newton's equations don't apply anymore.
You need Einstein's.
On a larger scale, there's also possibility that even classical physics does not work endlessly.
So as far as we know now, I mean, both of those come from Einstein. I mean, if you go to very massive scales, like massive as in like weight, I mean, it's not weight, it's mass, then you have to go to the general theory of relativity, which was formulated by Einstein and which is what governs things on a cosmological scale, like black holes, etc.
So I think
There's an example here.
at that point, even classical physics stops.
That stops means what? It does
Okay, I'll give you an example what you mean by probably classical physics stops, and what Shobhana said. The moment you go to the relativistic domains, it starts becoming different from what you see things classically. Say, for example, if you're sitting here and I walk around, you are seeing me moving, and I can go faster, and I can go even faster, and you can make that out. However, if you walk with me exactly the same speed, you see I'm not moving, right? Because we're moving together. But the moment it comes to light, the Einstein's theory of relativity says that in however fast you move, you see the light moving at the same speed. So in principle, that is already violating certain perception of classical behavior. So what Shobhana is saying is that what you say classical evolves to something is roughly where the relativistic domain steps comes in, and what we see around us becomes significantly different. That eventually leads to black holes and other general theory of relativity.
Yeah. But that's already well established. I mean, that's been, so we don't know of anything where that also breaks down. We don't. Well, we take that back. All these things break down in physical systems where we need both quantum mechanics and relativity. We don't know what that theory is yet. Right?
Well, I mean, this is what Stephen Hawking did. Just to add that, Stephen Hawking said there is something called quantum gravity, in which if you have lights moving in and there's a black hole formed, but the emission from black holes, he showed that the black holes, even if it goes way beyond classical, our classical perceptions, it still obeys quantum mechanics, the laws of quantum mechanics. As a result, that's where the whole idea of Hawking radiation came into play, that you can see what is. So he asked the question that classically, I'm not supposed to know what the black holes are, what is there inside the black hole. Quantum mechanically, I should be able to measure the Hawking radiation and still understand what's there inside the black hole. So there's a lot of debate, absolutely, without any doubt. But yeah, so it is very interesting physics.
So we don't have a theory of quantum gravity yet, right? So gravity, either we are talking of Newtonian gravity or we are talking of Einsteinian gravity, which is relativistic, right? General theory of relativity. But when it comes to describing gravity in the presence of quantum mechanical effects, we don't have a theory yet. Gravity is the only force of nature that has not been quantized. Right? The other three fundamental forces, electromagnetism, weak nuclear, strong nuclear, have all been quantized, which means they are described quantum mechanically. Gravity, we haven't succeeded yet. And there's still a debate about whether, open question about whether gravity can be quantized.
Thank you.
So this question is based on your slide. So you were saying that Schrödinger believed that wave function means this. Like, what is the he created the equation? So, what is the meaning of he believed?
Oh, at that time, I think what was, people were transitioning from thinking about physics in classical terms, where everything was continuous, to suddenly being confronted with matrix mechanics, which was showing that states of physical systems are discrete. You don't have continuous transitions, but transitions are discrete. So when Schrödinger came up with his equations, he was trying to restore the classical way of thinking, and he thought his formulation of the quantum state was actually describing something physical about the quantum system. And it turned out, that belief lasted literally a few months, and
What I was thinking is when he was writing the equation, when he writes, he should have a meaning for it, right? So, I'm writing this.
the psi is the state of the quantum system, right? So you can, but what that represents, he just wrote it, and I don't know the exact historical details here, but it's true that it was done as kind of a reaction to matrix mechanics, and it's called wave mechanics, and it felt very classical, and then it turned out that that psi, wave function itself, it was not a representation of physical reality in the way when we have variables in classical physics, those variables mean something. If there's a variable that says momentum, it means momentum that is continuously varying in nature.
Was it like the derivation of the equation was not driven by something physical, but something purely mathematical?
I don't know. Do you know more about this?
Yeah, I mean, I don't know, Shobhana. I have sort of read a little bit of historical development of that.
It's both. It's partly philosophical, but partly they're also trying to trying to describe measurements.
Yeah, actually, in the 1920s, when Schrödinger came roughly around mid-1920s. So at that point of time, there was this divide in the physics community that whether this is the whole idea of what you call a corpuscular theory. At that time, it used to be called corpuscular because that's the term which Newton generated 300 years ago. That, Newton said, Huygens said it's a wave. Newton said that it's essentially corpuscles or particles. And it's around that 1905 to 1920s, then people started thinking, okay, can this be both? So that's where Schrödinger was strongly in the believer of the wave part of quantum mechanics, and he used the wave theory to formulate the Schrödinger's equation.
But remember that he was the one who showed that matrix mechanics and wave mechanics are the same, right? So within months of him coming up with supposedly a classical version of whatever they were doing, he realizes that actually Heisenberg's matrix mechanics and his wave mechanics are describing the same thing. They're just different ways of looking at the problem, which then brought into question what the interpretation of that quantum state was. And then Max Born comes and says, hang on, it's not representing something physical.
One small question is, like, you mentioned that this experiment was in 1980s, right?
Which one? The one that, 1985.
So small question is, like, what does it take for Nobel Committee to give out the prize? Like, why does it take so much time? You mentioned that there are some applications around computer now, but in general, why does it take so much time? Like, do they wait for something that after this?
Who knows what goes on inside their heads? I have no idea.
So it's supposed to stay confidential, I think, for 50 years or something, what they do. But in general, it does take quite a while nowadays for work to be recognized with a Nobel Prize. There are a few exceptions, like this scanning tunneling microscope that Anil mentioned. I think that was awarded within 3-4 years or something like that. But
Even quantum Hall effect won 4 years.
Yeah, so, but I mean, Nobel's will, where he set up the Nobel Prize, said for whatever has had the most impact in the previous year, but that's not always true.
My suspicion is that it's because of the hype over quantum computing in the last few years, and this is the precursor. This is why we are even talking of quantum computing.
But most people were very surprised by this particular Nobel Prize. I think people didn't see it coming. It wasn't an obvious choice.
No, but the reason behind it is, this is the year of quantum. This,
This is 100 years of Schrodinger's, Heisenberg's wave non-matrix mechanics.
But in 2022, they gave the Nobel to quantum because to prove the quantumness of the reality around us. So they didn't want to say that this is the quantum Nobel Prize. So they restructured the term and said it's a macroscopic quantum tunneling. So it's essentially to show that something more fundamental, physics oriented, rather than a technology.
One more way we can think of is the idea which came then was far ahead of time. Only now people have started understanding the impact of that idea. So it was
usually always that case. In fact, I think John Clarke was asked during the Nobel Prize press conference whether they had realized the import of what they had done. And he said, absolutely not. We had no idea. We were just doing something. And
having fun.
like Chandrasekhar's 1929 thesis, which got him in 83.
Yeah, it can take a long time. Yeah.
Even Max Born, whom he mentioned, he got it like way, way later.
And
always say, what Socrates said 3,000 years ago, we are understanding today.
And remember, Einstein got only one Nobel Prize, and that too for his photoelectric effect. He did not get it for special relativity. He did not get it for general relativity. And so
to prove that also, they took 14 years for a total solar eclipse to happen. And to prove something experimentally, it will take time. So
yes.
Though you have a hunch, even gravitational waves, recently we got proved.
Yeah.
So the smallest particle you considered in quantum mechanics will see the photon of electron, you said. So where does string theory leave this thought?
Oh God, string theory.
So string theory essentially goes way below and baryonic matters. So you have quarks, and then you have the different flavors of quarks, which makes the nucleons, the nuclei.
Well, electrons are still smaller.
No, I mean quarks are smaller.
No.
Because it goes
in
inside.
what
No?
sense?
Are we going to fight
Physical. I think she asked for the sizes.
I mean, how would you say? I don't know. How would you say a quark is smaller than an electron?
Okay, because let me justify myself. The electrons are essentially wave packets.
It's great, right, to see us fight.
No. So electrons are wave packets, right? I mean, what you should. Typically, an electron will be given by, if I take the technical term of Fermi wavelength, A0, which is okay.
But the
I'll give the number.
Of an electron
I'll give you the number. It's about a
the
nanometer.
mass of a quark.
It's 1 nanometer. About say 10 nanometer is typically 10 nanometer is you take.
the spatial extent.
Spatial extent. I thought that is the question.
Function. But the mass of an electron is much less than the mass of a quark.
That is true. But I thought the question was at size.
Yeah, what do you mean by size?
But they need not be size and mass are two different things.
But I always think quarks are smaller than electrons and strings are like this.
So strings are way, way, way smaller. Okay. So, and first of all, they are hypothetical, right? There's absolutely we are nowhere close to being able to do any experiment that can verify that strings exist. They're way, way, way smaller. And the basic idea there would be that it's the vibrations of these strings, the vibration modes of these strings that eventually gives rise to the particles that we see, right? And one of the big complications with string theory is that it is not mathematically consistent unless you postulate that space-time has something like 10 dimensions. So 3 of the large dimensions of space that we experience and 1 of time, but at every point in space-time, there are 6 other dimensions that are curled up so small that we cannot experience them or detect them. So the entire theory is 10 or 11 dimensional space-time, depending on which version of string theory you take.
Well, that's
what
the
the
big
CERN
problem with it, because
Yeah.
there is no
Experimental
experimental
verification.
verification of it. Like,
So we'll have to go back to his question then. And the fact that you're working with neuroscience also, so don't you think it can somewhere lead to understanding consciousness if you can combine all that?
that's totally Anil's question.
I mean, I wouldn't bring string theory into that yet because physicists are themselves not sure of string theory, so no point bringing a theory that is not experimentally validated yet. I mean, it is an extremely amazing mathematical edifice. It's if you talk to string theorists about the math, they really think it's one of the most beautiful things from their perspective. And it solves some of the theoretical problems that physicists encounter, like quantum gravity. There is a quantum gravity, theory of quantum gravity from the string theory community. Is that the correct one? We have no idea whatsoever, right? So given that physics has yet not told us whether that's the right theory, there's no point using that to talk about something like consciousness, because on the neuroscience side and on the philosophy and theology side, we can't even agree on what consciousness is, right? Let alone have experimental measures to detect it or measure it. So definitionally, we have a problem. We have sort of philosophical issues about whether consciousness is something immaterial, like non-material, not immaterial, but non-material. Right? So we are material beings, but we are obviously conscious. So if you go back to whether you go back in theology, or to somebody like Descartes, there have been dualistic ideas of consciousness that we are made of matter and consciousness is some other substance. So there's what's called a property dualism. Substance dualism. Substance dualism is more or less gone out of the window. You would be hard pressed to find any neuroscientist or any scientist willing to say that there is substance dualism when it comes to consciousness. Theologians, yes, there's plenty of theological schools within religions that will have all sorts of opinions. But in science, right now, the debate about the nature of consciousness is mostly about the materialist perspective, which basically says that all there is matter. And yes, we have this internal perception of our consciousness being something non-material, but that perception is an illusion. And what we have to explain is why the illusion arises, not why there is something non-material. So that is one school. I'm being very stark here, and there is another school which says that yes, we are material beings, but there's something about the complex dynamics of the brain produces consciousness, which when it emerges from this complex systems has properties that cannot be reduced anymore to the material workings of the brain, which in physics people would call it strong emergence. And honestly, there is not a single instance of strong emergence in physics. Everything is what's called weak emergence, where in principle whatever emerges can be in principle reduced to the workings of the material world. In principle, we may not be able to do it computationally, but in principle it can be. But strong emergence, it's as if something emerges and then detaches from the material or the thing from which it emerged. Some people would say that consciousness is like that. Again, there is no empirical evidence to back any of these things. If anything, at least my personal view is that functionalism, materialism is on the right track. That there is, what we have to explain is why the illusion arises, not that there is something there to be explained. So given that, we don't need string theory. If string theory is right, it will just explain more of the workings of the material world. It doesn't have anything to do with consciousness.
It's great to know all this, but I meant that there's a way without experimenting to understand stuff. So that's what I meant. To understand string theory, now that we can't experiment at that scale, can we just somehow understand?
Well, that's what the physicists, but that's what they've done, right?
So let me tell. So there are efforts now to find what you called the analog systems, in which, so if you want to go to string theory or understand the baryonic matter, the particles, very small scale in terms of this energy, very high energy particles, then you have to go to CERN, where you collide particles and create new particles. The Higgs boson was kind of detected through those activities. Now the problem is that's a very expensive thing. I mean, running CERN is tens of billions of dollars a year. So what people are doing now is that they're trying to find out analog systems which can mimic some of the physical properties of matter at that level. Okay. So, for example, there are theoretical suggestions that high temperature superconductors can actually have properties which mimic certain properties of not only the baryonic matter, the quark, the gluons and things like that, as well as some property which is at the black hole level. So now there's a very strong activity to find out such analog systems on tabletop experiments. Okay? With that, certain theories probably can be checked, but there will always be debates whether that's really represents what's happening down there. But at least that's the best we can do at this stage. Otherwise, we need the kind of energy levels that CERN requires to go farther and farther in smaller and smaller particles. It looks impractical at this stage.
It's also a question, I would say, of what is physics and what is mathematics. Like physics, at least to me, by definition, is that you can measure things. If you cannot measure it, it is not physics. So to me, string theory in its present form is not really physics because you cannot measure anything. But it's beautiful mathematics. And beautiful mathematics is also very beautiful and is worth doing because sometimes mathematics, beautiful mathematics is made for its own beauty, and very unexpectedly later you find that it is useful in physics. But at present, I would say, to me, string theory is not physics. It tries to explain the physical world, but it does not lead to anything we can measure. And I feel, I mean, I'm of the school that believes that if you cannot measure it, it is not physics.
And one good example of what Shobhana is saying is quantum physics itself, right? You have to go back to when Paul Dirac, who got the Nobel quite soon after his work in quantum mechanics, one of the key figures in the formalization of the mathematics of quantum mechanics. When he was asked, is all this stuff in quantum mechanics going to be useful? He said, absolutely not, pretty much, right? 1930s. Everything, every smartphone that we are holding, this projector, just about every piece of electronics in this room is quantum mechanics. Wouldn't work without it, right? So, yeah. And also, weirdly, nobody would say, I guess people would say, but most people would say quantum mechanics is not beautiful mathematics, but
no,
sorry, no.
It is beautiful.
Yeah, maybe it.
I have a fundamental question about this quantum itself. What if matter just in observable form is quantized, but what if it's actually not? Like in every observation, it just likes to be in a minimum size of half. Can you show that it actually cannot be?
So what do you mean then, what if it is actually not? What does that mean?
No, meaning all of this is, like you said, it's all measurables. So what if we can only measure energy to that quantum, the smallest unit, and we're just not able to measure it below that? Does it actually mean that energy can only exist in those forms?
But we can measure below it.
Can we?
If it is not in those forms, yeah, we could measure it. I mean, see, remember this, all these things are happening in parallel with theory. Like for instance, the photoelectric effect. The photoelectric effect itself was experimentally verified before Einstein came along and theorized about it. It was a theory that explained why that behavior is what it is, right? So you might be observing something and you want to explain it theoretically, and you realize that the only way to explain it is if energy is quantized. So it's not like matter is doing something else and only showing us one aspect. No, I mean that was the experimental data that we had.
It's not a problem of resolution. It's not that we cannot resolve below this. We can resolve below it.
What if matter has some kind of energy has some kind of affinity to that unit, and that's just how it shows up on readings, and anything below that is just not measurable, or it doesn't exist on any detector.
I mean, look.
No, but there is, right? If you take a certain frequency of light, theory would argue that for that frequency of light there is a quantum of energy beyond which it can't go. For a different frequency, that quantum is much lower, right? So for this frequency, your instruments are saying, okay, there is nothing below this. But it's not like you don't have instruments to below the much smaller quantum also. If this was hiding something about the lower thing.
No, I'm not talking just about the instrument's resolution, but I'm talking about like the way that energy or packets of waves tend to behave. What if like we haven't been able to produce such extreme conditions, maybe at the center of the sun or whatever it is, that it maybe doesn't behave in this way. Like, is it possible, or is it like?
I mean, like finally, like Shobhana was saying, finally it's about our observations of the physical world. Are there things in the universe that we haven't figured out? Of course, right? But for everything that we can observe and everything that we can measure, etc., we have experimental observations, and we need theories to,
It's the best right now.
Yeah, I mean, at every stage of science, this is the best we can do, right? Doesn't mean it's the end, right?
Sorry, one more question. Sure.
I think, yeah.
I have an engineering question here, because we are talking about superconductivity as absolute zero resistance or something like that. If that is the case, how do we really make use of these voltages, currents?
How do you make use of?
Voltage, current.
Voltage, currents.
Because we basically have the Ohm's law is used for that relation.
So at the end of the day, you use the voltages and currents to measure the state in which the superconductor is in, right? If the resistance, if you pass a current but there is no voltage that develops, the resistance is zero. That means it's in a superconducting stage. If that is not the case, you measure a certain voltage, then it is in a normal state. Now, when
your question about
how do you make use of voltage and current?
How do you use it for an application?
To get any application out of this, we usually need a power source.
Yeah, but you have the current still. It's the current you want.
So like one obvious thing would be, if you have high temperature superconductivity, the superconductors that exist at room temperature and are scalable, easily manufactured, you can make your transmission lines with high temperature superconductors, and you have current just flowing through without any loss whatsoever.
So what we actually need is not the voltage, we need the current, and you get the current.
Yeah, we can control, and we need to control at many times. It depends on the application, but we can certainly use current and modulate it or change it, increase, decrease, and we have all the necessary equipments for that. And those are used in the superconducting, say, quantum computers and various other applications, of course. Yeah.
But those quantum computers are, they are at very, very low temperatures, right? So they are not room temperature things. So logical qubit is just a logical operation that you might want to do. But in order to build a logical qubit, you may need more than one physical qubit, because errors accumulate in quantum qubits, and you have to figure out a way of error correcting. So you need redundancy. So I don't know how many physical qubits on average you need.
It depends upon the qubits.
Depends upon the type of qubit.
Superconducting qubit, which it has changed in 2010 or 12. It was about 10,000 physical qubits will make one. But now the Google and IBMs are producing extremely high quality qubits. So now it has come down to about 1,000-ish. At least in the next 5-6 years, hopefully this will go down to about few hundreds. Then we have a serious number of logical qubits.
I have a question about the qubit. So like we know the bit, traditional bit, has a resolution of like 2, or like it can hold like 2 states. And is there something called like resolution when it comes to qubits? Like, because you have 1 or 0 and then you have superposition. So superposition can be defined as 2 probabilities, or 1 probability and the other. How many decimals are we talking about? Does it matter? Are we encoding like to a certain precision? And do different supercomputers distinguish? Like, are there some more precise, some less precise? Yeah.
So there is no, that way you can have, in principle, infinite number of states. between 0 and 1. Alpha, you can put as many z point after that, as many decimals. There is no resolution per se. There is no theoretical limit. Right. So that depends upon how you make this. So, for example, in order to make the state come to a particular superposition value, you need to apply what we call certain radio frequency pulses. So you send a pulse, the state rotates. Now, obviously, how closely you can get those states will depend upon how accurately you can send those pulses. So this starts becoming dependent on the equipments and other kind of resources that you have. But fundamentally, there is no limitation about resolution.
Pulse spread.
The pulse spread, yeah, that's correct.
But we would eventually talk about that, because right now I guess it's such a basic stage.
Usually that is not really the problem. That is not the problem, how accurately you want to place it. The problem is that the qubits, once you place it, it quickly loses the quantum length or coherence because of its interaction with the surroundings, and it loses the quantum information. So I can place it with almost as accurately as I want with the kind of equipment that we have today. But it soon loses that information. So in order to make a logical quantum computer, you need to then keep that quantum information intact. And that is essentially what a physical to logical qubit is. So physical qubit, you keep it there, then you use many other qubits to quickly understand where this one qubit is. And then you use error correction and various other protocols to ensure. Of course, I mean, entanglement is one of the basic ingredient there. Yeah.
So, how do we know that's actually whatever you're trying to achieve, this superposition? How do we know it's achieved? We just make random readings and then see the...
That's a good question. Actually, that's a problem, because for small systems which we know and simulate the answers of, that we can verify. But tomorrow, if there is a really complex system, very large number of qubits, and you run the computer and you get some answer, it's very hard to know what the answer is right or wrong, particularly in predictive aspects.
Not simple stuff, not yet. Right? Thank you very much.